Now let's look at another application or two here. Okay, so example 9. In meteorological studies, atmospheric temperature depends on the altitude according to the function T of H. And this, I'm using function notation here, getting a little ahead of where we are in the book, but this is our Y value here, and the notation is temperature as a function of H. It's just a place to put the input. So T of H is equal to negative 3.5 H plus 58.6, where T of H represents the approximate Fahrenheit temperature at a height H in thousands of feet. And it's going to have multiple parts, but first of all, interpret the slope. So numerically, it's negative 3.5. It's in y equals mx plus b form, but we're using h for the variable. So my slope is negative 3.5, and my units are the units on my output over the input, which would be degrees Fahrenheit per 1,000 feet. So I always say if you can get the units on your output divided by units on the input, and you can use the word per for the division, and then just read that and you almost get the interpretation. My slope is negative 3.5 degrees per 1,000 feet. So for every 1,000 feet increase in altitude, as you go up 1,000 feet in altitude, the temperature, the atmospheric temperature, is going to decrease by about 3.5 degrees Fahrenheit. It's negative, so it's going to decrease. Part B, determine the temperature at an altitude of 10,000 feet. So at 10,000 feet, our H is measured in 1,000 feet, so we would plug in 10 instead of 10,000. T of 10, we just plug into the formula, negative 3.5 times 10 plus 58.6, which gives me negative 35 plus 58.6, which comes out to be 23.6 degrees Fahrenheit. So we can evaluate the function is what we call that. Part C, we're going to have to solve an equation. If the temperature is negative 15 degrees Fahrenheit, so the output here, what's the approximate altitude? So we can plug the 15 in, negative 15 in for the temperature, and we get negative 15 is equal to our formula, negative 3.5 H plus 58.6. And we need to solve that for H, so subtract 58.6 from both sides. You get negative 73.6 is equal to negative 3.5 H. Divide both sides by negative 3.5, and we get that H is 21.029. I rounded to 3 decimal points since this is thousands of feet. So if I wanted to be that accurate from the formula, we have 21,029 feet. But it's approximately 21,000 feet. Okay, another application here, a linear model. In 2011, a man bought a used car for $14,500. In 2013, the car had depreciated to a value of $11,000. And we're going to do several parts here. Okay? But let's do parts A and B together here. We need the slope and the y-intercept to write the line, so we might as well do them together. So find a linear model for the value of the car X years after 2011. So that means we're going to start with the points 0 and the value in 2011, 14,500. So we're going to let x equals 0 be 2011, and we have our y value there. And then 2013, that'd be x equals 2 years after 2011, and the value was 11,000. So that's our 2 points. And for the slope, just go to the slope formula, y minus y over x minus x. It's going to come out, I've actually got a typo, I've got too many negatives there. It comes out to be negative. If you do your y minus y over x minus x, you wind up with negative $1,750 per year. And so the interpretation, there you have it, it's negative $1,750 per year. The value depreciates or decreases by $1,750 per year. The y-intercept is always your value at 0, and we're letting 0 be 2011, so in this case it's the initial value of the car, how much the man paid for the car. That's also the 2 numbers I need for my formula there. Y equals mx plus b will give me y equals negative 1,750x plus the initial value, $14,500. Okay. Then let's look at parts C and D. Part C, how much will the car be worth in 2015? Okay, so we need to subtract off 2011. We're measuring from 2011, so that would be 4 years later. So we need to plug in 4, so we get our slope, negative 1,750 times 4, plus our y-intercept, 14,500, and compute that, you get $7,500. So if this is the information, in 2015, 4 years after he bought the car, it's now worth $7,500. Part D, if we follow this model, in what year will the car be worth $2,500 according to the model? So that's the output of 2,500. We set that equal to our model that we found on part A, negative 1,750x plus 14,500. Subtract the 14,500 both sides, we get exactly negative 12,000 is equal to negative 1,750. Divide both sides by the slope there, and you get 6 point something. Okay? We want to know in what year, so we add that to 2011. It's 2017 point something, so it would be in the year 2017. And then there was one more part. Is the equation valid for x equals 25? Why or why not? Well, if we want to figure that out, we can plug it in. We can think about it. Should we predict 25 years into the future? But if we plug it in, what happens? You get that your y value, the value of the car, would be negative 1,750 times 25 plus 14,500. Well, that comes out to be a large negative number. Okay? So it doesn't make any physical sense. Okay? So physically, no. The equation's not going to hold. Once it goes past zero, the equation's no longer going to work. We call that extrapolation. Whenever you use a value that's far away from the x values you're starting with, or in terms of time here, if you use a value too far into the future. In statistics, we call that extrapolation. But definitely wouldn't work here because it physically just doesn't work. And then to summarize what we've looked at in this section, lines, if you move everything to one side, we call that the general form. Every line can be written as ax plus by plus c equals 0 for some coefficients. We had the particular cases, x equal to a constant is a vertical line, y equals to a constant is a horizontal line, and then our slope-intercept form, y equals mx plus b, and then the point slope, y minus y1 equals m times x minus x1.